And if you then tip your telescope to a different angle, you get a different fan across the sky. So you see the fan in this sort of greenish white, and another fan behind it, which is in color. Now, it's hard to see 3 dimensions looking at a 2-dimensional sheet, so I'll show you a movie that shows you first, you'll see the structure of the survey, and then, ignoring the structure of the survey, you will see how the galaxies themselves seem to be distributed. And the problem with the survey is this limited exposure and brightness. So here it seems to be fewer galaxies. That's just because they're so far away, you can only see the very brightest ones. There are actually as many galaxies out here as there are in here. And you will see the galaxies are not uniformly distributed, but they come in large aggregations and groups. There are big places where there are no galaxies, other big places where there's large collections of galaxies. So here's the movie. So it's rotating around, and you can see places where there are no galaxies, huge voids, and places where there are many galaxies together. When there are a lot of galaxies that get together, we call it a cluster. When there's very many galaxies together, we call it a supercluster. And occasionally, we see even a bigger connection. So here, you see this string of galaxies. It's actually a wall of galaxies. We call this the Great Wall, right? But it's not, you know, the Great Wall in China is more like a line. We're talking about a huge sheet of galaxies that stretches across the sky. It has millions of galaxies all arranged in a big sheet. So this tells you something about it. Now, there's one other survey. This Lone Digital Sky Survey has mostly been done by people in the United States, but with collaborators from other places. There's a European survey that's gone called the 2-degree field of view. And we're going to do a fly-through. Okay? So remember, it takes light 2 million years to get from one galaxy to the next. So we're going through very fast. But you will notice you can see some galaxies are spiral, and you can see its color. Some galaxies are elliptical. Anytime we have the knowledge, we have now a database of 1 million galaxies where we have not only their locations, but some of the properties of that galaxy. Right? Now we're going to swing out and look back at the survey. Right? It would be very nice if we could cover the whole sky, but we're only in the beginning stages, and it was a big effort to find the location of 1 million galaxies. We have to automate it. But now you can see the wedge, right? And you can see the fact that there are volumes where there are no galaxies and other volumes where there are very many galaxies. And here, this is part of the Great Wall. This is a different slice in the sky, but the Great Wall extends over a large region of space. The size of this volume, for example, is on the scale of 50 to 100 million light years. That is, light would take 50 million years to cross that void where there's no galaxies. So you see very complicated structures where there's no galaxies and there's filaments and there's other things that are out there. And so that's our rapid tour through the universe. But remember, this is the local universe. This is only our local neighborhood. It's like trying to judge the Earth by only driving around in Malaysia. That's the sort of the scale that we're talking about. It's actually only driving around this city to judge the whole universe. So what we do now is we do simulations to try and estimate what it is. And we have to take into account the universe is a little more complicated than we thought. We've worked for many years, that is, physicists and scientists have worked for many years to understand the matter around us. And we thought we understood it, and then we discovered there's another kind of matter. The matter we've been studying and making accelerators and so forth is no more than 20% of all the matter in the universe, of the kinds of matter in the universe. But in fact, at least 80% of the matter in the universe is something we call dark matter, which has very different properties, and we've never made it in the lab, and we've never made a direct detection of it. But we can see its impact and influence, and we're hoping in the next years, for example, in November or when the Large Hadron Collider in Geneva turns on, we'll begin to get some hints. We'll begin to be manufacturing them in our own laboratories. But if you look on the large scale, you will see the universe is very uniform, but when we zoom in, we'll see it's not at all regular. So the floor here looks pretty regular. It's not exactly regular, there's sort of random plinking, but on the large scale it looks pretty uniform, and it's semi-random, but it's not that random compared to the way the universe is going to be. So now I'm going to show you 2 movies. One is the plan view of the universe, where you zoom in, you see a slice of the universe, and you zoom in from the large scale to the small scale, and you see what the universe looks like. Okay, so this is a simulation, a Millennium simulation with 10 billion particles in it. This distance from here to here is about 5 billion light years. It would take light 5 billion years to go across that region. As you zoom in, you go from what it looks very uniform to where you see what looks like a web. And so the dark matter, which you normally cannot see because it doesn't interact with light except through gravity, is shown in white. And the ordinary matter that is shown in this color that looks like the sun, it's the thing that can actually coalesce onto the dark matter framework and produce stars and galaxies. So we're zooming in where many filaments come together in this cosmic web. So we have a large cluster of galaxies here, between 100,000 and 1 million galaxies in this region. Now we're zooming in more and more. Pretty soon we'll be able to see the distance between us and Andromeda. So now you see a small pair of galaxies here. That's like our galaxy in Andromeda in terms of scales. So we don't live in a huge cluster. We live in a very small cluster of galaxies. Our galaxy and Andromeda galaxy are the two biggest galaxies, and there's 20 to 40 very small galaxies that are clustered around us, but we're pretty much alone. But here we're zooming back out. So here, 5 billion years. 5 billion years for light to travel across this kind of distance. On that scale, the universe looks very uniform. When you zoom in, it looks like a biological system. And it's a combination that lots of stochastic things happen, as probability accidents happen, that generate this pattern that on the average comes out correct, but individually produces interesting kind of events like galaxies and clusters of galaxies and so on. So now we're going to fly through it. It's much harder when you're inside the universe to understand it than when you're looking at it from plan view. But you can see we're flying through, and the white is the dark matter, and the yellow is the ordinary kind of matter like you see in this room, and that make up stars and so forth. And it is able to dissipate energy by sending out light, and therefore collapse and form stars and form galaxies, and also be visible to us. So you see the white making the halos. It makes the structure. It provides the gravitational potential well that the ordinary matter falls into and then produces stars. So you see that kind of a structure, and you see the galaxies coming by, and you see we're traveling at a tremendous speed. And again, the people who made the simulation, this movie, of course, want to go and see one of the most rare and interesting objects. It's just like tourism. You go to the really strange things out in the universe. And you see where many filaments come together. And you see, in fact, that it's not static. This is a frozen time in the thing. But in fact, these clusters will eventually merge into that cluster. It will slowly move down, because you have to, even moving at a noticeable fraction of the speed of light, it takes millions to billions of years to move that kind of distance. Okay, so now we can do simulations to see how this came into being. So this is a simulation of what happens if a universe that only has dark matter in it. It's also a relatively small volume. The gravity has to take the initial perturbations that we see. And what I didn't tell you was those sound waves that we see at the beginning of the universe are just like the sound waves on the sun, but they're very small. The amplitude is only a part in 100,000. The universe is nearly perfectly uniform at the beginning, but it has these very small variations, and gravity has to work for billions of years to create these larger scale structures. And so what happens at the beginning is you have an almost uniform universe with these very tiny variations, but as gravity works, the places where there were fluctuations that were slightly high, galaxies will form first, and then, or places where galaxies will form first, are clusters of galaxies, and then you build up this cosmic web. So let me go back and show you the movie again. You see first spots appear, and then the spots connect up, and they make like a three-dimensional spider web, but a kind of a random spider web. We call this the cosmic web. This is the framework in which the ordinary matter then is able to collect and make the stars and galaxies that we see. And mostly in the pictures you saw, you couldn't see individual stars, you could only see galaxies. Okay. So we have a simple model there where we can do the simulation. The previous simulation had both dark matter and regular matter in it, so you can see it. Now we do even more complicated simulations. They're very computationally expensive. They take thousands of processors running for weeks in order to make them. So here is one that sort of traces out the whole history. It's a wedge that goes all the way to the cosmic horizon. That is the beginning of time. The beginning of time is out here, and the present is in here. And as we look out with our telescopes, we see back. And at the beginning, we're making the elements, we're making the pieces, but the universe is very uniform. except for these tiny variations. But over time, as the universe cools down, then we go from the region where everything is a uniform soup to the point where we begin to see the first structures, and they get more and more built up and complicated. So we have this period in which dark matter dominates, and the universe is slowing down, and structure is formed and evolves. And then we have the accelerated universe start, and that freezes structure formation. That is, anything that hasn't already formed and is starting to evolve, it doesn't get a chance to, because the universe is expanding faster and faster, and gravity can't keep up, and the universe expansion gets ahead of it. So here's the same picture without all the writing on it. So you can see how, as we look back, a billion years, 8 billion years, 12 billion years, 13 billion years, we see a very different universe in these spheres that we look around us. And this is our prediction of what it should look like, and we can compare that to our observations. Looking into this region is very difficult, but we have some new techniques that we're trying to use in order to understand that region. So we're in the period of great discovery about the very beginning of the universe. The satellite that I was responsible for putting the team together and all the pieces together, the Kobe satellite that made the initial discovery, this is what the map looked like when you take out a best estimate of our galaxy. If it had flipped over and looked at the Earth, you would have made a map of the Earth that looked like that, which might remind you of the maps we had of the Earth in the time of the great explorers, right? But not the way we have now. This is the best map we have of the sky. This is the WMAP map. This is the best map we have of the sky. The features are the same, except now you can see more details. There's more resolution in terms of what's going on. And this is a map of the Earth that you would have if you have the same resolution that the Planck satellite will have. And you'll see there's a huge difference between the way the Earth looks and the way the universe looks, right? So you see very clear features that are evidence of geology. You see this shape here, the shape of the Mid-Atlantic Ridge, the shape here. Clearly, there are forces that had the continents together and moved them apart and shaped them. Those forces we know are not linear forces, and therefore they couple things together and make those kinds of shapes. Where the early universe, we're able to show all the forces that were involved in the making of space-time up to this point are linear to at least a part in 10,000. So we see variations that are a part in 100,000, and you must go down to another factor of 10,000 below that before there could be any effects that are nonlinear, that second-order kinds of effects. So we're learning something about the processes of the actual creation of the space and time that tell us that it was a very simple system, very linear system, that we can try and understand very straightforwardly. So I want to sort of conclude this part of the talk and go to questions by showing you again this model of the universe, which when you first see it seems kind of strange, but when you study it and compare it to what you see in the universe, actually explains all the feature. It calls for us to have new forces and new knowledge, but it actually explains to us and allows us to calculate how the universe should behave with great precision, and is confirmed and to a high level, and tells us we have exciting times ahead of us, both in cosmology and in basic physics, to try and understand even more about the universe. So thank you, and I will stop at this point, and we can have people ask questions.
Hello, sir.
Yes, hi. What's your name?
I'm Ahmed Bashir, and I'd just like to say first that it's truly an honor to be talking to you. So welcome to UTP, first of all. I wanted to ask you a few questions. First of all, I was wondering what actually happened during the Dark Ages?
All right. Well, we call them the Dark Ages because there are no stars and no galaxies, so there is no light being emitted in the usual way of stars and things like the sun. But during that time period, the framework with the dark matter already exists, and the matter is spread very uniformly because of light pressure. So the example I usually give, if I took you and put you in the sun, what would happen to you? The answer is you would get burned on the way there, but once you got to the sun, electrons would be stripped from your atoms in your body, and the light pressure from the sun itself would spread your atoms across into a big cloud in the sun. If you did that to a galaxy, it's even more spectacular what happens. So the matter is extremely uniformly spread, the ordinary matter is